It's still good morning. Good morning, everyone. So here's my name. It's too complicated for everyone to repeat, and I know that. Not for everyone. Neither all can pronounce it correctly. You can call me Chris, or KK, or whatever sounds like this. It rings the bell. So I was asked by Carlos to talk about the mobile eye tracking. So I brought one mobile eye tracker with me, and I have it on me right now. And so you are recorded by now, and my gaze as well. I hope you don't mind. Doing live demo is always tricky because it never works. So I think maybe there's 1% chance that I'm lucky and it will work. Anyway, you can see my eyes, which are moving now. We have a lot of problems with my glass because of my glasses. They interfere with the cameras, which are trying to capture the position of my eye. So let me go with my story, like from the beginning. And let's talk about the eye tracking, what the eye tracking is, and why we do the eye tracking. And then let's look at the applications of mobile eye tracking. And this is what I mean by mobile eye tracking. I think I will take it off for my personal comfort. I'm sorry for this. You're going to be able to use it later on. It's still trying to capture the eye. So we will start with some basics. I will go quickly through this because I know you are all quite knowledgeable about the eye tracking. And but then I would like to build a ground for talking about the applications of mobile eye tracking in human-computer interaction. And then we have like 6 or 7 paths of applications, and I'll try to quickly go through these paths and show you the examples of the real studies which happened and which were published, and which have very different types of applications of eye tracking. Because eye tracking is not okay. I have to stop here and at least for a moment. So, by the way, I need to acknowledge that this is the output of OpenAI when my friend Adam Selary, who is running a fantastic eye tracking startup in Warsaw, you can, with his solution, you can do the eye tracking online. So that was the acknowledgement and advertisement. But he asked OpenAI about the history of eye tracking, and this is the outcome. And I found them quite beautiful, so that's why I put it here, and they are quite accurate. But the history of eye tracking really starts in 19th century. I don't know whether you knew that. And it started with such a creepy device, which they put on the eyeball, and then with some wheels here and a pencil here, they were able to draw actually the trajectory of the eyeball when the eye was moving. And that's from Edmund Huey's book from the end of 19th centuries. It was quite uncomfortable. So they thought that maybe it's smarter to use the cameras, which will look into the eye, but to have the good vision of the eyeball, they recommended to, in the beginning of 20th century, recommended to use the stripes to push the lip up and down. I really wish we still use them, but we cannot anymore, unfortunately, because of the ethical boards. So the real trackers really look like that. That's from 1935, and this looked like medieval torture machine. I know. So the hands were tied of the person, and the head was also screwed. So the lady, which is a participant of the study, of Baswell Laboratory in Chicago, couldn't move the head, just the eyes were recorded with cameras. Then they developed quite a bit more advanced systems with more cameras, but still nailing the participant to the device. And now, surprisingly, they got really good results. Really not much far away from what we can get right now in 21st century. This is the outcome of, this is scan path of eye movements from the Baswell book. And with one of these devices, he was interested in how people look at the art. And if I was repeating his study, his procedures with the current eye trackers, I would expect to have very similar scan paths. So nowadays, the trackers are much more user-friendly, and we call them remote eye trackers because we don't stick anything to the participant head. They have very different forms, like this here. This is iLink from SR Research, or that one, which is SMI eye tracker. Eye trackers stick below the computer screen, or these small babies from Gaze Point company. You can use them on the mobile laptops also. And that's a picture of our students taking part in the experiment, learning the eye tracking. So everyone is sitting with his own eye tracker, and there's an undergrad lab for undergrad students. All of them work in a pretty the same way. So first of all, there is the infrared illuminator. The bigger it is, the more accurate the picture of the eye is. Some lenses and high-speed cameras behind them, and that's a core. You have to illuminate the eye with the infrared, and then with the high-speed camera, record the eye position. In the infrared, the eye tracker sees your eyes in this way. And this is because of the infrared lighting and infrared filters, because the major point here is to capture the pupil. And whenever the tracker can see the pupil and the corneal reflection, it can actually measure the position of the eye in the outer world. That's a corneal reflection, and the difference between the corneal reflection, and the pupil, middle of the pupil calculated from the image, is something how the tracker is tracking the position of your eye. And it works for remote trackers and for mobile trackers, and the video eye tracking works in the same way. I have to acknowledge this gentleman, Furkinie, was a Czech anatomist and psychophysiologist who's really built the grounds for current psychophysiology. And he came up with he works in Prague and in Breslau. That was the old name of Polish town, which is now called Wrocław. He came up with the idea, and he actually proved that we have, when the light comes to the eye, we have a couple of reflections of this eye. And the most important for the tracking the eye position is the corneal reflection, the first one, which is on the outer side of the eye. So then the relation between the corneal reflection and the center of the pupil is something what allow us to measure the position of the eye. This is how the eye looks like in different settings. As you can see, if we have the infrared light and infrared filter on the camera, the image of the pupil is absolutely the most visible and clear. So it's easier to our algorithms to know where the middle of the pupil is. Without infrared light, it's all dark. Without filters, it's kind of blurry, so it doesn't make sense. And even with these small mobile trackers, you will see we have cameras which are pointing at the eyes. And next to them, there is a small infrared lightings, which reflects the eye. What makes it, I mean, this is necessary, but it has also the downside, because it makes hard for the eye. If you light your eyeball with a strong infrared light, it gets dry, and it can cause some discomfort and pain. So me, when I'm testing my procedures in the lab, and usually you have to debug your procedures for long hours, my eyes are crying because they're getting really, really dry. And that's a downside because we cannot really, with this technology, we cannot really say that this is something what we can use for live logging. So you cannot wear this technology for an entire day and be safe.
Yeah, so what's the time frame in which it's comfortable people barely notice they are wearing?
With such a small lighting like here, it can be 2 hours. With big illumination, like I show on SR research, these are super high-speed eye trackers, and this infrared light is really strong. So it is like half an hour, and after that time you are quite uncomfortable. All right, so that's an image from SR research, and here you clearly see the corneal reflection in the middle of the pupil detected by the tracker, right? So this is exactly how it works. To capture the image by video camera, detect pupil, and and then we have to map the coordinates of the visual scene onto the image of the camera and the pupil and the middle of the pupil. So that's the next step, and it's called the calibration. We map it because usually we present everything on the screen, and we use the most often used scenario is to present something on the screen and then attract the eyes. Because we know the dimensions of the screen, and we know exactly where we present something on the screen, we can quite accurately measure what we call the calibration error, the distance between the actual position of the eye and that's here, and the target, which is displayed on the display, right, on the screen. Before we starting measuring, we always do the calibration of the tracker. So we try to make this error as small as possible. It's always there, but we try to keep it below half of the visual degree, which usually translates to 1 centimeter or even below the 1 centimeter. It's quite harder with the mobile trackers, but still the calibration is, in most cases, needed. There are quite new advances in this technology, and some new trackers and new algorithms, which are based mainly on AI. They say that they don't need the calibration. There's a kind of a new product from the same company, Pupil Labs. They are called the Pupil Labs Invisible, and look like Ray-Ban glasses. They say that they don't need a calibration, and they can work for a couple of hours during the day. Really good product, but it's entirely related to AI. And actually, when you get into the technical details, they don't measure the position of the eye, they don't measure the position of the pupil, but they're trying to guess it or estimate it, it's a better word, with the AI algorithms. Yeah, that's why because it's built for a different purpose. It's built for longer logging of the eye position and being able to go outside and insight with the changes of the ambient light, which is of course influencing the measurement when you try to measure the exact position of the pupil. So AI is somehow overcoming these problems, but it causes different problems. And the different problem is that with this new pupil up invisible, which of course cost more, you cannot measure the size of the pupil, which is, you will learn in a second, is kind of an important measure, an important metric for us. So with the trackers, when we're talking about the quality of eye trackers, we're talking about the accuracy and precision. So nothing fancy here. This is the classical example of what the accuracy and precision is. Of course, we want the highest accuracy and the highest precision as possible, so that we measure at the target the gazes, and all the gazes are stable in time, right? So that's a goal. And with a good calibration and a good trackers and a good settings of the study, it is possible. So how does it work with the mobile eye trackers? This is not fake camera. This is not AI. Now I have to always explain what is AI product and what is not. This is a side comment. You all know that thanks to social media and the fake news and all this, everything what's going on with the media and journalism in the internet, now we have this phenomenon which is called distributed denial of trust, right? DT. And now with AI advances and VR advances, people expect that we will experience distributed denial of cognition, DDC. That's why I will explain always what is AI and what is not. That is real. This is how the eye trackers mobile eye trackers may look like. And the first mobile trackers were actually helmets with cameras pointed to the eyes. Then when the time passes, they make it on baseball hats, and now they do it as a glasses. Actually, it's such a simple device that you can build it by yourself for cost like 35 euros. I can really recommend, if you can Google this Mantube paper. It's an excellent paper, and then this like almost like IKEA instruction how to build the eye tracker from the webcam and all photography film, which is a filter for infrared. And one of my students, and this is so simple and good that one of my psychology students who had low experience in technology took the paper and built such a tracker in a week. I said, you don't have to do it. I mean, we have these devices, you can use them. No, but I want to try how it works. He did it. We still have it in our lab. So if you want to do something, you can buy a couple of cheap equipments. Maybe the most expensive would be the old webcam and some infrared diodes here, and stick everything together, put it on some old frames, and that's it. And there are open source software for this. Actually, Pupil Labs, which you buy in a store, they use this open source software as well, and it's called OpenEye. It's easy to Google. Right. So what we have on the shelf, we have a big players glasses, Tobii glasses. This is a big company. So you buy good hardware and good software. And my best guess is, because I never worked for them, but my best guess is that this price 20,000 euros comes from mainly from the software. Which is Ergonis is the company of the same size as, almost the same size as Toby. Ad hoc, that's amazing new company, and I can really advertise these trackers because it's completely different technology. They don't use cameras at all. They use kind of a sensors, light sensors, and a laser pointer, which is directed to your eye and can measure and does not make any harm to your eye and can measure with a extreme precision and accuracy the position of the eye and also the pupil size. They're quite pricey, but I think it's worth to spend money. Pupil Labs, excellent company, quite affordable. I remember a couple of years they started their prices with 500 euros. Now the cheapest is 5,000 euros, and depending on the device, it's going up. Yeah, but as I said, you can still build yourself the tracker, and people from Professor and Kaleda Kasnetsi, they build their own trackers with tiny cameras, tiny surgical cameras, which was quite of a successful tracker for 500 euros. I think you can buy from them. I'm not sure about it, but I can. So, okay, we know that we can track the eyes, how it works, but why? And that was AI. This is a history of eye tracking by OpenAI, and that's real. Why we track the eyes? Because actually, when we gaze at a point in the space, our field of view is super limited. We clearly see up to 2 degrees from the center of our gaze. And we have to move the eyes quickly to see the entire screen. All the that's called foveal view. Right here, everything is everything else is somehow blurred. And the further from the center, the more blur is in our image. So to see the screen, the mobile screen, you have to make a couple of eye jumps to build the entire image in your mind, right? So what we actually see is the effect of our internal AI, of our cognition, not the measurement of our eye vision. It is important because if we have something in the peripheral vision field, it doesn't mean that we cannot notice that. If anything familiar is here in this area, something what I tend to use every day, I can still recognize it. It's blurred, but I can still recognize it. Just like when you see a friend walking towards you in a fog. All right, so if it is a good friend, you will recognize him or her without a clear vision of the face of the person. And that applies also to our vision of the world. If we read, we still have the same role that we clearly see what we gaze on, but when we read, we see the other words in the peripheral vision. So if we proceed reading with our eyes, if there is a familiar and a short word on the peripheral vision, probably we do not have to fixate on it, but we can recognize it and speed up the process of reading, right? So when we talking about the eye movements, and such a typical scenario is that we fixate to have the clear vision of these 2 degrees around the central point of gaze, and then we jumped our eyes, we move the saccade to the different location. So fixation saccade, that's a standard. This is a standard sequence of our eye movements, right? By the way, again, a side note that our eyes are the most often moving part of our body. Even heart is moving not so frequently as eyes. And that includes sleeping and those periods when in a sleep when we don't move eyes. You know, REM, at this time, we move the eyes as well, even if we sleep, right? And these movements make sense. These movements are important and they are really interpretable. They can come up from our internal goals, needs, and motivations, or requests from others. They can be controlled by higher cognitive processes. When Yarbus asked his participants, that's a book from '67, so he had 3 participants in his lab. Can you imagine now submitting the paper with 3 participants and then being called a classic? So he asked, he showed to his participants the same picture by Ilya Repin's Unexpected Visitor, asking people different questions. How old are people presented? How old the characters presented on the picture? How long the visitor was absent? What's the relation between these people? How wealthy they are? And the eye movements really represented were very different and represented very different instructions, different goals, right? We replicated on a few of our students the eye movements by Replin, his findings, and we asked the student how old the people are, and you see his or her gaze path. You see that it focuses mainly on faces. So when we want to recognize the age, we have to focus on face, and it's just reasonable. So what eye movements represent? They represent what you ask for. And that's somehow clear. There are several different types of eye movements. Eyes never stops. And even if we fixate on a single point, it is a movement because it's a type of a movement and it's called fixations. Because if we fixate on a certain point to see these 2 degrees of visual field clearly, the eyes are shaking and they do it very small within fixational, it's a hard word, movements to stimulate the neurons on our retina constantly to change the lighting to have a vision. Otherwise, we got blind. So we have the fixations, saccades, the most important eye movements. One I would like to also point out here is a smooth pursuit, which is, I will show you in a moment the examples how it is used. The smooth pursuit is such a constant eye movement when you want to follow somebody or something. When I want to follow my hand and stick my head still, I do the slow eye movements. That's called smooth pursuit. So I still keep the vision of my hand, but I don't do jumps like I would do with fixations. Okay, one more point here. Vergence movements. These are quite funny movements. They tend to, their main reason is to keep focus and keep focal vision on the object which is moving towards you or away from you in the same direction. And now when someone in the real world is coming to me, like something like my hand, what I have to do, what my eyes have to do, is to accommodate, so have a clear vision with, and accommodation is done by the muscles around the pupil, to have the clear vision on my hand, and then my eyes have to do something like this or this movement. So convergence or divergent movements, right? And that's something what we learn. This is the mechanism of the keeping the vergence and accommodation together. That's something what we learn, and by the age of 6, we fully develop this link between vergence and accommodation. So eyes are trained to do this. But then we become teenager and we go to the 3D movie cinema, and we have to do something completely opposite, because we have to keep the with the 3D movie, and the same applies to VR. We have to keep the accommodation on the screen, but then we have to move eyes like the characters and objects would approach us or go beyond. And this is the decoupling of this is what is called decoupling of vergence movements and accommodation. What in fact cause you a headache and all this discomfort which is related to watching 3D or the extensive use of VR, because we're faking our brain. I will not stop on this any longer. There are fascinating papers on this. I can, today I can send you a couple of the titles, which are really good to read. So fixations, their main goal is to stabilize the image on the fovea of the eye, and they usually last like 250 milliseconds. Depending on the task we are doing, this is about a quarter of the second, how long the fixations last. They can be as short as 80 milliseconds, and they can be as long as 800 milliseconds. And the saccades are jumps between the fixations. What's funny that during the fixations, we really clearly see the image, and we can cognitively process the image. But during saccades, anything what comes to our retina is blocked. So from the psychological point of view, we're talking about the saccadic inhibition. So when I move, and when I do the jump of my eyes from Carlos to Marta, let's assume I can do it quickly. I won't see anything what is between you. I can notice that something is there, someone is there, but I cannot recognize it because I do not process, right? So now imagine that the aliens will come and they can read our neurons and move or show up only when we do the fixations. It's not my idea. It's John Watt's idea. He has a sci-fi book which is called Blind Vision or something like this. That the aliens came and all the astronauts have the feeling that someone is on the space station but couldn't see anyone. So when it comes to the back of the eye measurement, how we see fixations and saccades in the measurement of the eye. So actually what you have from the eye tracker is two columns of numbers. One is representing the position of the eye on the vertical axis, and the other is representing the position of the eye on the horizontal axis. Horizontal and vertical I show differently. And the third column is showing the timestamp, right? So you can easily plot it in this way, in this technical way. Now, this is the y-axis, this blue line, this dark line, and this is the horizontal axis. And the red is the speed of the eye, which is easy to calculate from these numbers. So, and that's it. Nothing else comes from the eye tracker. Sometimes when you turn on the plugin which can detect the fixations in real time, you can have additional columns telling you whether this part of the data is a fixation or a saccade, right? So here we see clearly that this person was actually reading. So his eyes were moving from left to right, and then coming back to the next line, adjusting slightly to the next line in this vertical axis, and again coming back, again coming back. Here we see saccades, and that's it. That's a different example. Oh, this one is of reading of the same text with a couple of hyperlinks in it. It looks completely different, right? Very different. Maybe not completely, but what we noticed that people were, instead of, we gave the same instruction to the participants, read the text and remember. That's it. And here what we noticed that they started to read the first line, then started the second and jumped to the hyperlink and gazed at the hyperlink like something was there. Probably they were wondering what's behind this hyperlink. Shall I click it or not? And jump back to the reading, so it's much more messy. The signal is much more messy. Then we, having the position of the eye and the speed, we translate it into fixations. Using one of two algorithms. One is basing on the disparity of the positions of measured eye positions, and the other is basing on speed. Whichever you choose usually gives you a good estimation of where the fixations are. Like here, we see three fixations A, B, C in the three different positions, and that's the same. I mean that's very similar to what we saw on the other slide. And we end up, when we have the fixation and saccades, everything between, we treat everything between fixations as saccades, so we can end up with such an image. And we have a circle that's marked the fixations and connections, saccades. The bigger the circle is, the longer the fixation lasts. And here is the important link between the length of the fixation and cognition. Knowing from Jas and Carpenter from 1982, they stated their hypothesis. It's not a theory because it's too small. They stated that the longer we gaze at something, the longer the fixation lasts, the more cognitive processes are going behind it. So we better process what we gaze at. And there is a clear connection between attention and gaze. So this is what they say, if I gaze at someone, I process the image of this person. If I gaze at something, I put my attention there and I process cognitively what I see. Some of current researchers say that this hypothesis and this link does not apply to two populations, students mostly, and husbands talking to their wives. I don't know, maybe. So when I gaze at something, I usually see it and process it. I know that it sounds like, okay, anyway. And the last eye movement I want to talk is the pupil dilations. If we measure the pupil position and the pupils, we can measure usually pupil size. You can do it with these trackers. You cannot do it with newer pupil labs trackers because they do not actually measure, they estimate by AI. And this, our pupil is working constantly to keep the accommodation and keep the clear vision as well. It mainly reflects the changing in the lighting. And this has to be said. So whenever it's lighter, it shrinks. Whenever it's darker, it puts more light into the eye, so it dilates, right? But it was linked as well with the cognitive processing and cognitive load. When Hess and Paul in 60s, they gave their participants the mental arithmetic task. They noticed that the harder the task was, the pupil size on average get wider. Like 2 by 2, no changes in the pupil. Like 17 by 17, it's getting larger. 148 by 150, how much is it? Anyway, I just wanted to not see a pupil size. It's getting even wider, right? Right, when I asked I wanted to replicate this study from 60s with my current psychology students, and I gave them the task. Their pupil size get wide at the beginning and stayed like this for the entire experiment, unfortunately, because they usually have very bad experience with math, any math. This is what can happen. But yes, the larger the pupil, usually the more cognitive attention load is imposed. Also, the changes in the pupil was proved somehow they represent the or can be linked with the cognitive load. It's a quite a bit more complicated. The more changes in the pupil size, more high frequency oscillations in the pupil size, the more cognitive load we can expect in the person. And it can be as well, it applies as well to the intrinsic cognitive load coming from the internal processes like this math tasks, or it can be extraneous cognitive load coming, for example, from bad font when you read, or too speedy subtitles in a movie, right? So now when we're talking about accessibility, we should be aware that we can somehow input the cognitive load to the user, or we can take it out from the user, and we can also online measure the cognitive load with changing our displaying techniques, or applying different designs of the media to not overload the user, and to leave cognitive resources to process the content. This is extremely important when we're talking about the disabilities, cognitive disabilities. All right. So in a human-computer interaction research, how we use the eye tracking, especially mobile eye tracking. This is AI again. This AI pictures are more fascinating. Yeah, they're quite nice. So that's a graph I've stolen from the fantastic paper from my good collaborator and friend, Andrew Duchowski, gaze-based interaction, 30-year perspective. So what we can have, the gaze-based interactions in the research, we have assistive usage of gaze into the interaction, active, passive, expressive, and diagnostic, which is offline. And when I was talking about the cognitive load so far, I was mainly having in mind this diagnostic use of eye movements or eye information. Eye information, this term should be somehow, I should give a credit to Hans Witzner from Copenhagen Technical University, who coined that term. Anyway, diagnostics. This is the most often use of eye tracking to measure the eye movements and then diagnose the user, right? For example, the big field is comparison of experts and non-experts. They tend to have very different eye movements. And it includes the pupil size and includes the scan paths, so the sequences of fixation and saccades. When they compare the scan paths of experienced and non-experienced pilots, they look completely differently. Usually experts, when we read the literature on expertise and eye movements, we find the result that experts tend to have shorter fixations and longer saccades. So they tend to exhibit something what we can call more ambient scan paths, more ambient patterns of attention, because they don't need, because they are experts, they don't need much time to understand what they look at, right? And the same applies to doctors when they try to diagnose your pictures, chess players as well. But it does not apply to, and this is what, that was a kind of a discovery for me from the last year. It does not apply to experts in art, which was very surprising. We did a project on, and we are still at this ongoing project, when we're trying to build a accessibility technology for people, for blind and visually impaired people to sightsee the cities, actually. And first of all, we want to measure how the eye movements of experts and non-experts look at when they are looking at some historical units like buildings and monuments. And what we found out that experts tend to fixate much longer on the building, on the art. And expert, I mean architects and fine art experts or fine art historians, because on the building there are much more details to understand than on a cockpit. It can be surprising, but it is. And they need these long fixations and to connect what they see with their historical knowledge of how it was constructed, when it was constructed, what was the style, and so on. They build all the long stories in their minds when they look at something, while non-experts tend to just look at the building, well, or art piece, nice, okay, go. That reminds me of me when I was visiting the British Museum in London. So first I was just paying attention to every small coin there, and then I was passing these kind of elements from the pyramids, okay? We as non-experts, we don't understand so well as experts what we see. That's why they gazes are completely different. And we really measure the eye positions with the mobile glasses. So you can see some exemplary eye movements on buildings. This is the non-expert scan path on this building. Okay, let's go on. It's not so interesting. Anyway, if you want to read more, there is upcoming paper. It will be in ETRA proceedings from this year, when we somehow prove that non-experts scan paths are much more ambient than expert architects and art historians scan paths. And there is also a nice way to bind the scan paths of the entire groups, which, yeah. Now, when you have the ability to measure the eyes outside the lab, you can do it also when when you drive, and that's a fascinating kind of usage of the eye tracking, which was proposed by Ania Warchoł-Jakubowska, who's here, and this is her PhD project. She's measuring the eye movements in the tram simulators to compare experts and non-experts, and then on experts, on their scan paths, build the training for novice drivers. Because when you drive, of course, you have to learn all this technology, but you have to learn and train your attention. Otherwise, it can be very, very dangerous. And that was proved that basing it's not super new. I mean, it's new when it's applied to tram drivers, when it's applied to the real world. But the idea is coined somehow earlier, when they were trying to also teach the novice diagnosers, medicine students, basing on scan paths of experts, of advanced doctors, and they succeeded. There's a fascinating paper by Anne McNamara and her team. She's from Texas, but Raymond Bailey and is from Rochester Institute of Technology. They use the expert scan paths, and how they did it to teach the non-experts, the fresh students. They used something what they call the subtle gaze manipulation. So they didn't show the entire scan path, but that was like a subtle changes in the image. They built on the expert scan path, which was directing, without noticing even, the gaze of the fresh student. So the student was looking at the image, and he barely noticed that his gaze is actually directed, like by hand, where he should look at to find the disease, how big jumps he should make, and how long he should stay in different areas to find something wrong in the image. And I think the same idea will be used by Ania Warchoł for training non-expert or fresh drivers, which is fascinating. I cannot wait to see the results of this project. Yeah, there's a lot of applications of mobile eye tracking in sport. I know it's not human-computer interaction, but it's hard to not mention when everyone have seen probably this image of Ronaldo's eye movements playing football, and what they found out that he's not looking at the ball, and he's not looking at his foot, but he's looking at the target where he wants to go, and he's looking on his opponent to predict his movements. We did a study on sport with Peter von Stickskesser, he has a hard name, and we tested on kids, and we have a kids aged like 9, 12 years old from the football school. They did a test, that's a kind of a test when the player is in the middle, and he has to hit the different color targets, and he doesn't know the order of the targets. So the instructor is just telling him, okay, green, blue, yellow, red, in a random order, right? So they have to quickly move around and hit the target. So why we measured gaze? What we found out that the more they look on the ball, the kids, the worse performance was. The more they look on the other person, on the instructor and the audience, the lower performance was. If they look on the target, they were performing well. I planned, that was a study which was run a couple of years ago. It was, we only recently managed to publish this study in Journal of Eye Movements. But what we planned originally was that we were trying to follow up with these kids and see how they develop in the future as a football players, but we didn't, unfortunately. So that was my mistake. What's another application from the sport, which is quite interesting. I told you that, again, when you want to hit the target, look at the target. I told you that the fixations last between 80 milliseconds to 800 milliseconds. But it's not true. Sometimes when you are the Olympic champion in a shooting sport, do we have any Olympic champions here in the room? Carlos? No? I thought you raised your hand. They found this phenomena testing Olympic champions. They call it quiet eye, that they look at the target just before shooting, whatever, whether it is rifle or archery or whatever kind of a shooting or a ball. They look at the target for 5 and keep the eye fixated for 5-6 seconds. I thought it's impossible. I thought they make mistake. This is an artifact, but it's not. It's really, I mean, there's several studies replicating the same effect, and they call it quiet eye. This is what actually the champions what are taught in purpose. And that's another amazing use of eye tracking to diagnose and then to use the data for training, like they do with badminton, and especially the Korean national team is advanced in this. They capture and diagnose the eye movements of their champions and then move these eye movements to the new players. And they taught them, they have the cognitive attentional trainings, because badminton is, I don't know whether you like to play badminton, it's a super complicated sport and it's super fast. And super exhausting. It can be so fast that after 5 minutes, when I played with a good player, I almost died. And the attention have to go super quickly to the right point to make a hit. Otherwise, you just, okay, this video is not available, so let's move on. The other application is the active application, where you use the gaze and you capture the gaze in a real time, because when we capture the gaze, we can store it on the computer for the post hoc analysis, like we did previously on the previous slides. Now I'm talking about the situation when we capture the gaze and we can use at the same time we capture for interaction with the computer, and it's called the active applications. Like, for example, gaze selection, and the most popular is the use of the dwell time for selecting. I really don't like this slide. I'm sorry, I have to tell it, because it's ancient already. It comes from the WIMP word. WIMP is and WIMP approach. Windows icon mouse pointer. So the idea is to how to mimic the mouse pointer with the gaze. So how to make clicks with the gaze and move the pointer. Moving the pointer is quite easy, but then makes clicks with the gaze. And they said, okay, let's use the dwell time. So if person moves the pointer and dwells at a certain number for a second, sounds not long, it will make click. Oh, okay. But then when we use our computers, we make thousands of clicks. So when you add these seconds, it makes it unusable almost. In some cases, it works. with the very super simplified and specially designed interfaces, it works. The other technique, which is faster, is border crossing, which was in this paper, again by Duchowski. When only the eyes cross the border, the number was pressed. And this is an application in pin entry, the other applications on in eye typing. There are excellent applications of this anyway for people with movement disabilities, right? When you cannot actually use your hands or anything else for the keyboard, you can use your eyes and have a very dedicated interface. I pointed out the smooth pursuit movements. On this slide, I like much better than the previous one because it's going beyond the WIMP. It's in this approach of post-WIMP, right? When we don't have a pointer and clicks and selection. They developed the idea of using the smooth pursuit movements. So these movements which are tracking the objects, right? Or the smoothly relocating the eye position. What's interesting that with these smooth pursuit movements, you don't need to know the exact position of the eye. With clicks, with gazes, you need to know the position, so you need a great calibration. With these movements, tracker detected that you follow the dot here, it was making the selection of this item. Was this following was the smooth pursuit. We have 2 minutes to watch the authors, how they talk about the work, because I think it's so fascinating that I would like to give the floor to them. They call it orbits. Actually, they were using these trackers, which we are gonna have for play. I think you got the idea. So if interested, please have to say read the paper. yeah, the paper is really, really good. I'm going to share with you my slides. So the references to the paper are there on the slides. I'm going to send it to Carlos, and he will distribute it among you. The other application of the real-time gaze measuring is called passive. That was active for clicking or selecting objects, right? With dwell time or smooth pursuit. Here we have a passive application, which especially is applied to 3D displays, any kind of a 3D display, because our vision is, when we gaze, is limited to 2 degrees, and the rest become blur. So the idea of this application is, behind these applications, I should say in plural, is to keep the clear image only where your gaze is, and the rest actually can free up the graphic card resources, for example, or free up the computer memory and computational resources. It also was found out that such an application reduced the visual discomfort when watching the 3D displays or stereoscopic displays, I should rather say. It also applies to the dimensional, to the position of the eye, but also applies to the depth of field. So if we manipulate with the depth of field, so rather with the contrast in the center, we manipulate with the blur in the peripheral view, we can also reduce the discomfort. And what we found out, that's not my major topic, but I did one study on this. And what we found out that this manipulation with and use of the actual gaze for the depth of field in stereoscopic displays reduces this decoupling of vergence and accommodation movements, which I told you is one of the major reasons for feeling discomfort when watching 3D displays. So it's kind of a promising way to use eye movements as well, and this is called the passive application. And then the last one is expressive applications, which are used for modeling eye movements, and they use these models in the real media. The problem with eye movements is that they usually were modeled and are modeled in a way which is quite artificial, and it's easy to recognize that they are not human eye movements. And what was found out, not by us, but the others, that non-realistic eye movements is one of the major reasons why we do not believe the person or the character in animation. It looks artificial, we cannot like identify with the character because his eyes or its eyes are moving so artificially. One of the ideas how to change it was presented in this paper. We added to the animation of eye movements the small jitter. Like I told you, even if we fixate, we make a very tiny microscopic eye movements, or we call it microsaccades. So the idea was to add to the animation of the eye the jitter signal, actually, and actually that was it should move, yeah. This jitter was based on pink noise, because the pink noise somehow represents the noise which is observed also in our neurons. It has a kind of a memory in it, so it's not completely random. right? And when we add this pink noise, artificial pink noise, we did this user study, and that was one of the most funny studies I've ever done, because we were presenting a couple of such an eye movements, such an close-up images of the eye to the participants and asking them to evaluate how natural they look like. And some of these animations were with the jitter, with a different amount of the jitter. Some were without. And anyway, people evaluated. We're doing something like a forced to two choices task. And when they came up, 80% of my participants, when they came up from the lab, they say, "Why you were asking me this question? How they natural look like these eye movements? They all look the same. Or maybe one was different." I said, "Okay, so maybe it doesn't make sense." I was quite frustrated after this. But then when I look at the results, so behavioral results were clear, absolutely. They really recognize the movements with the jitter as more naturalistic. So that was, again, this phenomena that people sometimes don't notice. They say, "I don't like it," or "I don't see the difference." But then the real measurement tells that it's completely different. Just like this was also visible in this. Yeah. Okay. There are many examples like this. So let's. I'm going to skip a couple of slides because
complex decision making with large screen collaboration.
Sorry. There are a couple of more slides with a couple more references. So if you're going to be interested, please look at the slides, read the papers, or contact me. I would be happy to answer any questions. Now, these babies are going to be with you for tomorrow. So it's quite simple to use. It's enough to plug into your computer. Everyone can download the software. It's free, as I told you. And there are quite simple instructions on the Pupil Lab website how to use these trackers. You put them on. You have to adjust the eye cameras. I will not do it right now because I have glasses and you need a bit of time to do it carefully. But please be careful with these babies. They're quite fragile. And the next step, you have to learn the tracker. How they work. They build a 3D model of your eyeball. So first of all, when you wear it and you turn on the application, which is called Capture, you have to rotate your eyes alongside until the application will learn and build a 3D model of your eyeball. And then you can run the calibration and then measure the eye movements. Now, be aware. Yeah.
That's just a camera on the eye tracker. It's not used for eye tracking anymore.
Okay, that's a word camera, right? So this one is on you. And my two cameras on the left for my eyes. They are adjustable. ID 0 is the right camera. They did it completely wrongly. And ID 1 is on the left side. Anyway, so we have to see the clear image of the eyes of your participant and how to use it. When we be aware, some of you maybe have Macs. So when you have, is anyone with the Mac? Yeah. You have to have administrative privileges to run the application. Otherwise, these new Mac systems, they will ban from using the camera to measure eye movements. So have to run this line to start the pupil capture application. And And the pupil capture is actually what you see here. And when everything is good on these two, in these two spots, we see the measurement of quality of the eye. The greener it is, the better. The higher to 1 it is, the better. The 1 is excellent, 0 is no eye. Okay, and it's left and right eye, or right and left. So these are kind of the instructions. They're also visible on the Pupil Labs website in documentation. So if we have this image, then we can run. Then we can next run the calibration. Just pressing this C here or C on a screen on a keyboard, and then if my eyes were visible to the cameras, I should be able to calibrate, meaning that when I gaze at the point, it should get green and change the location to the corners of the screen. I will disable this one because it's not gonna work. And when we calibrate the tracker, then we can start recording. So pressing R is for recording. And here you go. I stopped recording. All the recordings are stored in, okay, I have to stop this application as well. All these recordings are stored in the folder which is called recordings, surprisingly. And it is in your home directory, right? So whenever I go to recordings, I mean, the structure of folders, actually, it's quite well done here, because in the recordings, when you start collection of the data, that creates the subfolder with the date. Today we have 16. Right, 16. And then the next subfolders are the numbers of the recordings of the day, right? And when I go to the first one, 000, is all the data are here. Let's go to the last one, which is just we took a second ago. Oh, 002. And here we have the images of our eyes in MP4. It should be there, I0 and 1 and the word 1. And all the data should be there as well. But what I need to do is to analyze the data afterwards. So I just followed the instruction, drop a recording directory into this window. So let's do it. And this is my recording directory, 002. I will drop it here. I have to proceed with SMAC again. Okay, and this is what we recorded. No eye position because we did not do the calibration. So we did it wrong in this demo, but if you're gonna play, you can do it immediately. And if there is an eye position, you should see also the data set with the fixations detected and saccades detected in this directory, and the other data set, CSV file with pupil dilation side, pupil dilations done every timestamp. We have people who are quite an experts in this room, so don't hesitate to ask, work together. I mean, Kasia, Anya, I know them using the PP Labs glasses. Maybe others. So if you feel the expert in using PP Lab glasses, don't hesitate to help. I think that's it from my side. Is it me? Is it this? No, I have a couple of slides more. Okay. Okay. Consult the Pupil Labs core. This is documentation. And these are important slides. I really have to acknowledge people without whom this presentation wouldn't happen, like Ania Warchoł-Jakubowska, Patrick Szczeciński, he's there. Andrew Duchowski is not with us, he's in the States, in Clemson. And again, Kasia Wisiecka and Kasia Kuta, the other member of our team, Isa Krejtz, and who's more, and a couple of people who are doing, with whom we're building this accessibility system in the city center. Professor Pawłowska, Daria Siuda, art historians, computer scientists, and the other people like Morten Field and Birgit Kopański. All of them contributed to the content of these slides I showed you today. So thank you, guys, for talking to them. And thank you for your patience. And this is my gaze. No, it's actually the gaze of art historian and the computer scientist. Pictures are mine, but the gazes are of some exemplary, random computer scientist and art historian. You see the very differently. Yeah, the same. Okay, thanks. That's it. Time for lunch.
If you have any questions.